Hi everyone, here is an example of an Euler's method problem in which we're going to use a tabular setup in order to implement Euler's method in the solution of this problem. Here we are asked to approximate the particular solution to the differential equation y prime equals x plus 2y that passes through the point 0, 2. We are going to compute 5 steps of size 0.1. So the 0.1 is our delta x value that we will be using. This is a great example of a differential equation that we cannot solve by hand, which really what makes Euler's method very, very useful in solving a problem such as this. Hopefully you remember the formula for Euler's method. It states that a y sub n value is going to be equal to the previous y value that we denote as y sub n minus 1 plus f of x sub n minus 1 comma y sub n minus 1, which you will remember is our differential equation, times our delta x value. Now an alternate way I like to think of it is that the way in which Euler's method works is it is an iterative process in which each successive point builds off of the previous one. So I like to think of Euler's method formula as stating instead that the new y value is equal to the old y value, the one from which you are working, plus the value of the differential equation, your derivative, at that old value times delta x. Remember that this really is simply a linear equation that you're writing. It looks a lot like point-slope form of a line. dy dx, of course, is your slope. Your delta x is your change in your x's, the difference in the x's from one x value to the next. So what really all this is using a linear equation. So let's go ahead and get our table set up. The values that serve as our table headers really come right from that formula. In this case, we were told the initial condition of having the point 0, 2. So that is the point from which we're going to start. Remember what our derivative was. Y prime is equal to x plus 2y. And it is into that we're going to substitute these x and y values in order to get our dy dx value, our slope. So in this case, we get 4 for our slope. Now we need to do that slope value times our delta x. Remember, in this case, our delta x was given to be 0.1. So we have 4 times 0.1, which gives us 0.4. The new y value then, if you think of how the formula goes, is equal to your old y value plus the slope times delta x, and that equals your new y value. So if we do 2 plus 0.4, we end up with 2.4. That is now going to carry down to become the next y value from which we're going to work. Our next x value, remember our x's are going up in steps of 0.1. So that means the x value that's going to go with that 2.4 y value is 0.1. And we simply repeat the process. We're going to substitute into y prime to obtain our dy dx value, our slope. So substituting into x plus 2y, we here get a slope of 4.9. Multiplying that by our delta x, we obtain 0.49. And then finally adding together our old y value of 2.4 plus this product we just obtained, 0.49, we end up with 2.89, which once again becomes our next y value from which we're going to work. Our x's simply go up in increments of 0.1. Repeating the process again and substituting into our derivative so as to obtain our slope, we obtain a dy dx value of 5.98. Multiplying that by our delta x of 0.1, we obtain 0.598. And finally, adding together that old value of 2.89 plus the product we just found, we have 3.488. Now remember, we were to have done 5 steps. Essentially, when we got through that first line, that was our first step. Second step, we just finished our third. We're almost done. And then this last one will be our 5th step. And the answer we obtain from that will be our final answer. Substituting into our y prime equation, we get 7.276 for our slope. Multiplying that by our delta x of 0.1, we get 0.7276. And finally, adding our old y value to this product, we obtain 4.2156. That becomes the last y value from which we're going to work through. Substituting in to obtain our slope, we get 8.8312. Multiplying that by our delta x, and finally what we arrive at for our answer is 5.0987. You'll notice that we often extend this past our typical thousandths place, really just for accuracy. So the final answer to this question in terms of what the particular solution would be to this differential equation, given an initial condition of the point 0, 2 lying on the original curve, would be 5.0987.